We were talking about intermediates, electron displacement effect, inductive effect, and we ended up with the idea of Bronsted-Lowry. And then we said strength of acid is directly proportional to the stability of conjugate base. Okay, conjugate base. Okay, fine. So just to remind you guys of what we have learned in the last lecture, and in organic chemistry, general organic chemistry, where are we right now? We are at the phase where we can say that let us say like this. We have some acid, which I will say HA. Why HA? Because this is a protic acid. That means it is going to liberate proton. Plus, I will have a B with some lone pair electron. Okay, with some lone pair electron. Then what is going to happen? The A is going to leave the electron, so A will become negative. Plus, B will share its electron with hydrogen. This will get a positive charge. Okay, this will get a positive charge. Now, this is also not. I mean, not in each case you will get a positive charge. But what I wanted to say here is, A was 0. It will become whatever the whatever the oxidation state of A is there, it will decrease, and the oxidation state of the base, it will increase, right? It will increase. So let us say, imagine if we have HA plus B negative, then it will become A negative, and the B will become BH with a 0. So again, this is also an increment, right? From negative to 0, it is also an increment. From neutral to positive, this is also an increment. So generally speaking, there will be an increase in the oxidation state of the base. There will be a decrease in the oxidation state of the acid. This is our acid. It will get converted into, this is what conjugate base. This is conjugate base. Okay, this is conjugate base. Now we said the strength of acid, strength is directly proportional to the stability of A negative, that is the conjugate base of conjugate base. Okay. Now let us do a question. Compare the strength of following acid. Okay, strength of following acid. So here you have NO2, which is bonded to CH2. It is further bonded to COOH. This is carboxylic acid. This is obviously an acid. And we have to compare this with, let us say, if you have CH2, which is bonded to CH2, which is bonded to COOH. Then we have, let us say, fluorine, which is bonded to CH2, it is bonded to COOH, carboxylic acid. So you have ABC, and we have to compare this. Now, first of all, initially, you will never compare the acidic strength like this. Okay, we'll never compare the acidic strength like this because you're starting out right now. What you will do, you will disassociate the hydrogen from the acid. Okay, so please see what will happen. When it will show its acidic character, then it will become NO2, CH2 bonded with COO negative. Yes or no, guys? Tell me this. COO negative now, because H has been dissociated. There will be H plus ion. This is the acidic character. Yes. Okay. Similarly, what will happen here? CH2, which is bonded to CH2, and it is further bonded to COO negative. And here I will have fluorine, which is bonded to CH2, which is bonded to COO negative. Just wait a second, okay? Yeah. And here we'll be having H plus, and here also we'll be having H plus. Okay. Now, what we can compare is out of these three, which is most stable, and the one which is most stable, it will be what that will be forming very rapidly, and then we can say that this is the conjugate base now. So the acid of the conjugate base is the most strong acid. It's the most strong acid. Okay. So how will we compare this? First of all, you look at the charge. Number one step is look at charge. So tell me, is it positive or negative? Is it positive charge in the conjugate base or a negative charge on the conjugate base? Tell me. Hi guys. What type of charge is there here? In the conjugate base, this is the conjugate base now. No one is saying negative charges, right? Okay, fine, negative charges. So we want to decrease the negative charge. So we have negative charge, and we know that stability is inversely proportional to charge, yes or no? Stability is inversely proportional to charge. That means we have to decrease the charge density. Okay, rather than writing charge, I should write charge density, right? You remember now? In the last class, we did all these things, right? Yes. The charge density will decrease. How it will decrease? If we will have, so I can say it is directly proportional to the presence of electron withdrawing group. Now, what you need to compare is C. You know, don't compare whatever is similar. So this much part is similar. We have only difference in these parts: NO2, CH2, and fluorine. So what I will do, I will say the presence of electron withdrawing group. So which is the most electron withdrawing group here? It is NO2. It is the most electron withdrawing group. Directly this. Next is fluorine, and then next is CH2. Sorry, this will be CH3. My bad. Okay, CH3. So this is the order of electron withdrawing groups, and we have seen that. We have seen that acidic strength directly proportional to the stability of conjugate base, which is inversely proportional to the Q density, charge density, and this is proportional to the electron withdrawing group. Okay, now you can relate directly from electron withdrawing group and the acidic strength. Yes or no? We can directly write the acidic strength is directly proportional to the electron withdrawing group. That is why the order will be same as that of the electron withdrawing group. Okay, so we have, this is A, then C. This is A partner. This was in A, this was in C, and this is in B. So the order of acidic strength, order of acid, this will be A is most acidic, followed by C, followed by C, and followed by B. Okay, tell me, did you get this? Yes or no? Huh, guys, tell me.
Yes, sir.
All of you got this?
Yes, sir. Yes, sir.
Okay, fine. Now, you want to write this, or you have written this?
Written.
Written? Is there anyone who has 1 minute? Okay. Write one more thing you can write here. See the acidic strength, and if it is directly proportional to the presence of electron withdrawing group, that means it is what? It is inversely, it would be inversely proportional to the presence of electron donating group, right? So acidic strength, it will be inversely proportional to the electron donating group. So if there is more electron donating group, that means the negative charge will be highly unstable. The negative charge will be highly unstable. 1 minute ho gaya?
Yes, sir.
Okay. Next, right? Compare. Compare the acidic strength. So here you can have CH3, COOH, okay, and it's attached here chlorine group or fluorine group, okay, and B is if you have fluorine which is attached to CH2, so CH2, just further attached to CH2, and then you will have COOH. So in this case, we have the same. The electron withdrawing group is the same, but what is difference here? The difference is the distance, right? The difference is the distance. So I can say that acidic strength is what? It is inversely proportional to the distance of minus I group, right? Distance of minus I group. If I talk about the distance, then A is what? A has a smaller distance than B. This is the distance order. distance order, and the acidic strength will be just the opposite. That is why B का ज़्यादा distance है ना, B has farther distance, right? So the acidic strength will be just reverse. A is more acidic than B. Let me know if you understood this, yes or no.
Yes.
Distance of minus sign. Okay.
Yes, sir.
We did not write plus I groups, no? So you will write plus I group. Can I move? I think so, no?
Yes.
Let me know if you are not there. Okay. So now write plus I effect and electron donating groups. Now in electron donating groups, we will start with the negatively charged species. Okay, so CH2 negative, if you have, okay, CH2 negative, it will be having the highest plus I effect because it is negatively charged. It can easily donate electron. Okay, and also why it can easily donate electron, because carbon is not more electronegative. It is not very much electronegative, so it can easily give some electrons. Followed by NH negative, right? Followed by NH negative. Now you can understand the comparison between nitrogen also has negative charge, carbon also has negative charge, but the tendency to give electron is more of carbon and tendency to pull electron is more of nitrogen. And after that, you can also put the O negative, right? You can put the O negative. This will be followed by, if you have COO negative, let me give a punch like this, COO negative. This can also give some electron. This can also give some electron. After that, you will have a carbon, which is attached to 3 other groups, CS3 groups, or R groups also you can write in general. So this also has a tendency to give electrons. This will be followed by, if you have a carbon atom which is attached to 2 methyl groups or 2 alkyl groups. Next, you can write a carbon atom which is attached to 1 methyl group, okay? And at last, you can write a methyl group, CH3. So starting with some negative charges, the COO negative, and then we will have a carbon, tertiary carbon, secondary carbon, primary carbon, and then there will be methyl group, okay?
Done, sir.
Done? Okay. Now, if I compare question, compare acidic strength, compare the acidic strength. CH3, which is attached to carbon, it is attached to CH3, it is attached to CH3, and this is also attached to OH. This is attached to OH, okay, versus we have B structure, which is, let us say if you have just CH3, there will be a hydrogen here and OH group attached here. Okay, so here we can see acidic strength. It is what? It is inversely proportional to plus I, right? It is inversely proportional to plus I. Order of plus I will be, first of all, you will write only the order of plus I. So order of plus I will be A is the most plus I, followed by B and followed by C. So the acidic strength will be reversed because it is inversely proportional. So write A, then B, and then C. Okay. You understood this? Yes or no, guys? Tell me. Acidic strength part?
Yes, sir.
Okay, very good.
Done, sir.
All of you done?
Yes, sir.
Okay. Now let me just write a few points. Okay. There are two things. Okay. There are two things. There will be acidic strength. There will be basic strength. Okay. So acidic strength will increase if you have, sorry, if you have minus I group, if minus I increases, okay, minus I increases. Let me write it like this. Acidic strength is directly proportional to minus I, okay, and it is what? It is inversely proportional to plus I effect. Basic strength is directly proportional to plus I. Basic strength is inversely proportional to minus I. Okay, just the opposite. Let me know if you're done.
Done, sir.
Okay. Now write resonance. Now write resonance. Right, resonance. What is resonance? Right, shifting of pi electrons. Shifting of pi electrons or lone pair electrons within a compound. Within a compound. So initially we saw what is inductive effect. In inductive effect, what was happening? The sigma electrons were shifting. Here, what is happening? The pi electrons are shifting. Okay, the pi electrons are shifting. We have seen some type of resonance in the bonding chapter, right? Chemical bonding chapter. Same idea, but more examples. Right, resonating structures. Resonating structure. Resonating structures are hypothetical, and it is an intramolecular phenomena. Combination of all resonating structures is known as resonance hybrid structure. Resonance hybrid structure. Done?
Yes, sir.
Okay, see. Resonance also, like you can imagine resonance as similar as what I can say, reactions. Okay, it is a reaction. You can understand it as a reactions. What is happening? What happens? Let me take an example. Don't write this. Okay, CH2. You have a double bond. CH. There is a single bond, and then you have CH2 positive. Okay, CH2 positive. Can you identify the electron rich source? This is the electron rich source, right? Yes or no? Pi bond is electron rich. Yes or no?
Yes, sir.
Now this is electron deficient. Yes or no?
Yes, sir.
Now you have electron rich site and electron deficient site in the same molecule. Then what can happen? This pi bond will move over here, and it is going to form CH2, a single bond, CH, a double bond, CH2, right? CH2 here. The positive charge will go. The positive charge will come here because this carbon is losing one bond. Okay, it is losing one bond. That means it is losing one electron. If you lose one electron, that means what is happening? We are gaining a positive charge. Now, can you see that again? This can also happen. Similarly, here we have this as the electron deficient sign, and this is our, and what is this? This is our electron rich side. This is our electron rich side. Then what will happen? This pi bond will now move here. Okay, so this thing always goes on. Okay, it does not stop. It does not mean that this is different structure and this is different structure. Rather, what is happening? These two structures are same. These two structures are same. This is continuously happening. Okay, the positive charges here, positive charges there, and positive charges here and there, here and there, here and there. Now, what do you think? You can't even see a localized positive charge. It is moving so fastly, right? It is moving so fastly. What is the bond length? It is somewhere around 1.5 angstrom. 1.5 angstrom means 1.5 into 10 to the power minus 10 meters. So obviously electrons can move so fast that you can't even see a complete positive charge in either of the carbon atoms, So these reactions are very fast. Then what you will be seeing, you will be seeing something like this: CH2, CH, CH2. You will see some double bond character here. You will see some double bond character here. And you will see some delta positive charge here, delta positive charge here. If I am very precise, then I can say you will see a plus half of charge here, and you will see a plus half of charge here. Do you understand what is happening in resonance? Yes or no? Guys, tell me. Yes or no, guys, tell me. It is kind of a reaction only. Okay, you can understand it as a kind of reaction, but very fast reaction. In reactions, what happens? The electrons move, right? So the electrons are moving here also. It's just that they are moving very rapidly. They are moving very, very rapidly. So the bond breaking and the bond forming, it is what I can say. It is in a continuum. Right? So when it is in a continuum, then you can't identify which bond is single, which bond is double, which bond is single, which bond is double. So we say that partial double bond character exists in both the bonds. You understand it? Yes or no? Now tell me.
Yes, sir.
Okay. Wait a second. Okay. Now, right, conditions for resonance. Okay, conditions for resonance. Where the resonance can happen. So, right, conditions for resonance. Now, one thing will be always true, that is electron source to electron sink. Okay, so from electron rich to electron poor, you will be always shifting electrons. You will always be shifting the bond. The electrons from electron rich to electron poor. Right, conditions. Conditions for resonance. Okay, conditions for resonance. A resonance takes place when pi electrons are in conjugation. So for example, what are the cases of conjugation? You can write cases of conjugation. Now, these are the building blocks that you have to remember. These are the building blocks, simple building blocks of resonance that you have to remember. I will write both type of cases. For example, you will have pi. There will be a pi bond, which will be followed by a sigma bond, and there will be a positive charge there. There will be a positive charge. You can write this as A double bond B, right? A sigma bond C, and C has a positive charge. So if you see this type of building block, then obviously you have to recognize that there is a resonance here. Then there can be a pi bond followed by a sigma bond, then followed by a lone pair, electron. You can show this as A double bond B, single bond C, and C has a lone pair electron. Then you can show this as, another example will be sigma bond, and there will be a free radical here. There will be a free radical here. Now, you can show this as A double bond B, single bond C, and C has a free radical. Okay, this lone pair example, or you can also write this as A double bond B, there is a single bond C, and there is a negative charge. Okay, this negative charge will always be accompanied by a lone pair electron. Okay, always a lone pair electron. This is a free radical. This is a free radical. Free radicals are formed by homolytic cleavage. Okay, homolytic cleavage. Then you can also have pi. There will be followed by a sigma, followed by another pi. That is A with a double bond B, the single bond C with a double bond D. Okay, with a double bond D. Then also you can have a lone pair, right? You can have a lone pair electron, followed by a sigma bond, followed by a positive charge, followed by a positive charge. So what could be an example? What could be an example? You have A, right? There is a lone pair. There is a sigma bond followed by a lone pair. This is a sigma bond. Then there is a B, which has a positive charge, So these are the cases in which you can have conjugation and where you will be doing resonance 1, 2, 3, 4, 5. Let me know if you're done.
Done, sir.
Okay, and also one more thing, or this can also be written as A with a negative charge. Okay, now negative charge means there is a lone pair. Obviously, there is a lone pair. There will be B and there will be a positive charge here like this. Okay, so this is also one more case that you can write. Okay, now what I will do, identify the type of resonance in following. Okay, resonance in following. A. So, for example, let me show you. So what is this type of resonance? So this is what you have: pi bond, sigma bond, then again pi. Okay, this is pi sigma pi resonance. Okay, now you know how to answer. Tell me, Hishma, Mariam, Samaira.
Yes,
Okay,
sir.
okay, fine. Yes. Huh, guys, done? Tell me. You completed writing this? Yes or no? Samaira, Mariam, Hishma. Huh, guys? Yes, Mariam.
Sir.
You okay? Fine. So, Mariam, tell me for the B1, what type of resonance is there in the B1?
First case.
B, pi sigma
Oh, pi sigma and
positive, right?
positive.
Okay. Hishma, you tell me for the C. It will be pi sigma
lone pair.
pi sigma lone pair, right? Pi sigma lone pair or pi sigma negative, right? Pi sigma lone pair, pi sigma negative. Okay. What is the D1? Samaira?
Pi sigma positive.
Pi sigma positive. Okay. What about the E1? Who will tell me for the E1? Huh, guys?
Pi sigma pi.
Pi sigma pi. Okay. Anything else? Tell me anything else? Or only pi sigma pi? Oxygen has lone pair now. Yes or no? Ah, guys, tell me. There is a lone pair. There will be lone pairs on oxygen, na? Okay, so never. Yes or no? Hishma, Mariam, Samaira,
Yes, sir.
Ulsra. Okay,
Yes.
thank you. Okay, so we'll pi sigma lone pair. Now again here also we have NH2 which has lone pairs, right? Which has lone pairs. Nitrogen also has lone pairs. So please, Lewis dot structures, right? Lewis dot structure, very important Lewis dot structures. So we'll have here pi, then there is a sigma, and then we have the lone pair electrons. Then we have the lone pair electrons. What about G? Tell me about G. Yusra, tell me about G. What type of resonance?
Pi sigma
Pi sigma and
lone pair.
this was a lone pair, right? Oxygen, it always has lone pairs. Okay, if it has two bonds, it will always have lone pair. So this will be pi. Oops, sigma लिख दिया हमने. Pi sigma lone pair. What about H? What about H? What about H? Tell me. Huh, guys? What about H? Samaira, tell me.
Lone pair sigma and positive.
Yeah, lone pair. Then there is a sigma, and then there is a positive charge. Very good. What about the I1? We have here pi sigma and free radical. Pi sigma free radical, right? Yes or no?
Yes, sir.
Yes, sir.
Okay. Now what we can do? We can write the first structure, right? We can write, okay. We will have, let us say, A part. In this, we are seeing pi sigma positive charge, or we can also write this as A double bond B single bond C, and C has a positive charge. Okay, so you can just keep writing. This is the same example that we did just before. CH2 double bond CH single bond CH2. There will be a positive charge. What will happen? This electron will come here, electron source to electron sink, followed by a resonance. So these two reactions both are happening very fastly. Okay, very fastly. That is why we write this resonance arrow, and then we write CH2 single bond CH double bond CH2, and this will get a positive charge because it lost an electron, because it lost an electron. So both of these structures are known as resonance structure. Resonance structure. This is also resonance structure. Okay, and if we combine these two, then we will be getting what? We will be getting CH2 single bond CH CH2. So see, one thing is very constant here is the atoms, they are not changing the connectivity, only the pi bond is changing. And then you will draw what? Partial double bond, delta positive, delta positive. Okay, now another example you can write is of, if you have a benzene ring type of thing, and there is a CH2 positive. Then what will happen? This pi bond will move here, and it is going to make will be double bond CH2. Now this pi bond has moved. This carbon lost an electron. That is why there will be a positive charge here. There will be a double bond here. There will be a double bond here. Now again we can see pi sigma positive. So this will move this side, and again you will be getting a benzene ring. There will be a double bond here, CH2. The double bond has gone here. Now this carbon atom, earlier also it had 3 bonds with pi and all, and there will be a sigma bond. Okay, you can see 3 bonds here. You can see 3 bonds here also. So the positive charge will go here. There will be a pi bond here. Now again you can see pi sigma positive. So this will move here. Double bond like this with CH2. There will be pi bond here. The pi bond will be here. Will be a positive charge here. Again, pi sigma positive. So this pi bond will move here. You will get CH2 positive, right? Then there will be a double bond here. There will be a double bond here, and there will be a double bond here. Then again you can see what is happening. Pi sigma positive. Then again the same thing will happen. Okay, the same thing will be happening. So the resonance structure you can write. These are all the resonance structures. The resonance hybrid will be, if I combine all these, then I can write it as a benzene ring. There is a CH2 group. Okay, so this is something which is constant. And as you can see, sometimes pi bond is here, sometimes it is not this. Sometimes it is here, sometimes it is not there. So what I will say, the pi bond, it is moving in all of these. So we write a circle like this. Okay, you can also see, I mean, either this will be the structure, there will be some double bond character here also. There will be a delta positive charge here. There will be a delta positive charge here, here, and here. So delta positive, delta positive, delta positive. Okay, or you can also write the structure as okay. So both are fine, but okay, write this down. Then I will tell you one thing, and then we can move on.
Done, sir.
Done. Okay.
Done, sir.
See, we had this structure, right? CH2 positive, and there were double bonds like this. Now, if we did not know about resonance, and an untrained person in chemistry, a person who has not been trained in chemistry, if he saw something like OH negative, then what he will do? Oh, so easy. He will just attack here, and he will say, sir, this is the product. Sir, what is the product? This is the product. CH2OH, right? But now we know that this structure is not the complete picture. This structure is not the complete picture. What is the complete picture? This is the complete picture. So we have positive charges all over the places. We have positive charges all over the place, right? So OH negative, it now has chance to attack here. Also has chance to attack here. Okay, it also has chance to attack on the CH2. Now I'm not saying this is another thing, because this carbon and this carbon, they are equivalent carbons. So either it attacks on this first delta positive or the second delta positive, it is the same thing, right? So an oxygen has 3 products. Okay, it can form 3 products. It can be either like this, CH2OH, or it can be something like this, CH2 positive, and there will be OH here, or there can be CH2 positive, and there can be OH here, right? So there are 3 probabilistic products. The probability is how? Now this is something like chess, right? So if you don't know chess, then you can't say if you are in a winning position or a losing position. Similarly, if you don't know about resonance, then you will be missing many major things which are happening inside the molecule. Okay, many major things which are happening inside the molecule. Right. So this was just a taste of resonance and how it affects the reactivity and what kind of insight you will get if you know about the resonance. Okay. Chalo. So you have written till here, yes or no?
Yes.
sir.
Yes, sir.
Okay, fine. Now I'm giving you one more example. Please write this with me. B part, that is pi sigma lone pair, है ना? So you can write this also as A double bond B single bond C, and C has a lone pair, or you can also write this as A double bond B single bond C, and C has a negative charge with lone pair obviously will be present. So example will be CH2 double bond CH single bond CH2. There will be a negative charge here. So this negative charge, now obviously, which is more, which is higher in energy, a bonded electron or a non-bonded electron? Obviously, non-bonded electron, it is only attracted by one atom. Bonded electrons are attracted by two atoms. That is why non-bonded will move here like this, and this will move here like this. Okay, so you will get CH2 negative with a single bond, CH with a double bond, CH2. You can write the resonance hybrid such as CH2 single bond CH single bond CH2. There will be some double bond character, partial double bond character here, delta negative, delta negative. Okay, so write this down. Let me know if you're done.
Done, sir.
Done, all of you?
Yes, sir.
Okay, fine. Chalo. Thank you very much.